It's February 15th, 2013. In the quiet Russian city of Chelyabinsk, people woke up expecting an ordinary morning. Work, school, life as usual. But the sky had other plans. At 9:20 a.m., a blinding fireball, brighter than the sun, ripped across the sky at 19 kilometers per second. A 20-meter asteroid, no bigger than a house, exploded over the city. Seconds later, the shockwave arrived. More than 1,000 people were injured, most of them school children cut by flying glass. Windows shattered across several cities. The blast carried the force of 500 kilotons of TNT. 30 times more powerful than Hiroshima. Soon, the news was all around the world. No one saw it coming. No alert, no warning, nothing. And that terrified scientists. Within months, a group of scientists at the University of Hawaii, funded by NASA, launched an emergency project, an early warning system designed specifically to catch small, fast, deadly asteroids before they reach us. They called it Atlas. This is the story of Atlas. To understand what Atlas actually is and why it's so unique, we first need to understand what makes small asteroids so dangerous and so hard to detect. Small asteroids may be only a few meters or tens of meters wide, but they strike Earth far more often than large ones. And they approach at tens of thousands of kilometers per hour. They are too dim to spot early. They reflect almost no sunlight, and they may be visible for just a few days or even a few hours before passing by or entering the atmosphere. In planetary defense terms, these are the hardest objects to detect and the easiest to miss. And that's exactly what Atlas was built to do. Atlas is a network of small but ultra-fast telescopes that scans most of the visible sky every single night. It looks for anything that moves, brightens, or suddenly appears. Unlike deep space observatories that hunt faint galaxies, Atlas is built for cadence and coverage, seeing a huge portion of the sky and seeing it often. Atlas is built to deliver the last alert for incoming impactors. That means a few days of warning for 20-meter objects and a few weeks for something around 100 meters. As of 2025, Atlas consists of 5 0.5-meter telescopes, each equipped with a 110-megapixel camera and an extremely wide field of view, large enough to capture an area of sky about 100 times the size of the full moon in a single image. The first telescope was installed on Maui in 2015, and a second Hawaiian telescope joined the program in 2017. NASA funded 2 additional telescopes in southern hemisphere. By early 2025, a 5th Atlas telescope came online in Tenerife, Spain, giving the system near continuous global coverage. This geographic spread is one of Atlas's greatest strengths. With telescopes in both hemispheres, when it's daytime in Hawaii, a southern telescope is observing at night, so the sky is always under watch. Together, the network scans nearly the entire dark sky each night, processing around 250 gigabytes of data. It's in effect a planet-wide early warning radar for the cosmos. But how does a system like this actually work? Atlas works by scanning huge areas of the sky over and over again, looking for anything that moves. One Atlas telescope can scan the visible sky a little more than once per night, but the full global network allows nearly the entire dark sky to be imaged multiple times each night. The detection method is actually so simple. On a typical night, a single Atlas unit images about 1/4 of the visible sky and takes 4 exposures of every field, spaced 10 to 15 minutes apart. Atlas's automated pipeline compares these frames and detects motion, measures how fast an object is moving, and generates early estimates of its orbit. Potentially hazardous objects are highlighted immediately. Once a new object is flagged, Atlas automatically sends its measurements to the minor planet center. Observatories around the world can then perform follow-up observations. At the same time, NASA's JPL Scout systems uses the Atlas data to calculate impact probabilities. If there's any chance of a collision, the information is passed to NASA's Planetary Defense Coordination Office and to the International Asteroid Warning Network. This rapid reporting is crucial because many small near-Earth objects are only visible for a few hours or days as they make their closest approach. Atlas's job is to catch them before they vanish again into the darkness. But what really sets Atlas apart is not just how it works, it's what it was built to do. Atlas fills a very specific niche in asteroid detection, one that complements rather than competes with the giant observatories. Large surveys like Pan-STARRS or the Rubin Observatory can see incredibly faint objects deep in space, but they cannot scan the sky fast enough to catch small asteroids on short notice. Pan-STARRS, for example, with its 1.8 meter telescopes, is excellent at spotting big asteroids long before they come close. Rubin, one of the most advanced survey telescopes ever built, will scan the sky to unprecedented depths, but even it can only cover the entire sky every few nights. Its field of view is smaller and its observing cadence simply cannot match Atlas. In fact, Atlas sees 4 times more sky in a single shot than Rubin can, and that wide field of view is exactly what allows it to refresh nearly the entire sky every single night. These deep surveys take days, sometimes weeks, to complete a full sweep. Atlas sacrifices the ability to see faint, deep space objects for incredible speed and coverage. That's exactly why Atlas, not any other missions, discover 3i Atlas. As I mentioned before, Atlas is optimized to spot objects that are bright, fast-moving, or behaving in unexpected ways. So when 3i Atlas suddenly appeared, it fits that profile perfectly. Bright enough to stand out, moving quickly across the sky, and following a rare hyperbolic path. This means it was only visible for a short window before it was plunged out of our solar system forever. Atlas's rapid cadence was key to confirming this short window interstellar visitor. While 3i Atlas is the system's most remarkable discovery so far, it's far from the only one. In 2019, Atlas detected a small asteroid known as 2019 MO just a few hours before it entered Earth's atmosphere and exploded as a bright fireball over the northeast of Iceland on March 11. Beyond these headline events, Atlas has discovered hundreds of previously unknown asteroids, comets, and supernovae, contributing enormously to our understanding of small and fast-changing astronomical objects. Atlas is a simple idea executed exceptionally well. A network of modest, wide-field telescopes working together with fast automation to provide the last alert humanity might get for small incoming asteroids. It doesn't replace the giant surveys or deep space missions, it complements them. While powerful observatories search far into the cosmos, Atlas focuses on something far more urgent: speed, coverage, and the ability to spot danger in the final hours or days before the impact. After the tragedy of Chelyabinsk, Atlas was built with one goal: to make sure we're never caught off guard again. Its wide field of view and rapid cadence allow it to catch the surprises. From discovering 3i Atlas to detecting multiple Earth-impacting asteroids only hours before they hit, Atlas proves that even small telescopes can play a massive role in planetary defense. For some incoming rocks, it may be our first and last line of sight, and together with the world's larger surveys, Atlas ensures that the sky is never unwatched, and that next time, we won't be taken by surprise. That brings us to the end of our look at Atlas. If you learned something new today, please hit that like button. It genuinely helps the channel grow and tells me you want more videos like this. This was my first major long-form science video on the channel, and I'm dedicated to posting a new in-depth science explorations. If you want to join me on this journey into space, science, and technology, make sure you subscribe and hit the bell notification so you don't miss the next one. Thank you so much for watching all the way to the end. See you next time.